Hello friends, in crystallographic texture the last lecture in this particular module will be on application. Okay. So, what is the application of understanding of texture on one of the properties, that is what we are taking, okay, and that is what we have discussed earlier also, that when you are deforming or you are doing a deep drawing of any sheet material, okay, so there is a flow anisotropy. That means, if I take a, for example, let us take a material or a rolled sheet for example. Okay. So, this is my rolling direction, transverse direction and normal direction. So, basically I am taking a suppose I am measuring the tensile properties, okay, flow properties in this direction. So, I am taking a sample from here, and then so this is I would call as 0 degree, okay, and then maybe I will take another sample like this, okay, at 45 degree, okay, or maybe another sample like this parallel to TD, okay, that I will call as 90 degree, okay. And if I measure the flow properties in each of these condition, if the flow properties are same, okay, the ductility, the yield stress and so on, okay, then I have no problem, the material is isotropic, okay, and there will not be any problem in the formability of the material, okay. But usually the issue is that, suppose if I take a round blank like this and I am deforming it, okay. So, in the cross sectional, suppose it is deforming like this, okay, then okay. So, there will be thinning in this region, okay, because you are stretching the material, okay. This part will not deform at all, okay. So, if the material has different properties in different direction, it is a circular blank which we are deforming, what will happen, that in this direction suppose deformation is easy, but suppose in this direction deformation may not be easy, for example, or in this direction the deformation is not easy. So, what will happen, the deformation will take place in this direction, but in this direction the material will just get instead of stretching, it will be pulled by the punch, okay, if the deformation is not uniform throughout the sheet, okay. So, this kind of anisotropy develops what we call as earring phenomena, as already I have told you. So, in this direction the material is not able to deform, okay, but in this direction material is able to deform, okay. That is why you are seeing that the material got pulled by the punch, whereas in this case the deformation took place, material did not pulled by the punch, okay. But the other problem will always be there, that there will be thinning here, okay, it will get thin in this location, okay. So, one is the planar so this anisotropy, now I can divide into two different type of anisotropy, okay. The first is called planar anisotropy, and this planar anisotropy is the cause for this kind of earring phenomena, okay. And basically it is simply that the property in different direction is different, okay. So, that can be found out by a relationship like this, okay, delta R, where R is the if you are doing a tensile test, if I divide width strain by a thickness strain, okay, then that will give you R, the ratio will give you R, okay. And this width and strain ratio, if I determine for a sample taken from parallel to rolling direction, then it will be R naught, okay. If it is parallel to TD, that means at 90 degree to rolling direction, then it will be R 90, and if it is at 45 degree, then it will be R 45, and in these three direction we are trying to see that what is the this ratio width strain to thickness strain, okay. So, if you have a large value of delta R, okay, whether it is positive or negative, that means absolute value of delta R, because it can be negative also if R 45 is more than sum of R 0 or R 90, or it can be positive. So, if we take the absolute value of delta R, okay, without worrying whether it is positive or negative, then it indicates high planar anisotropy, which is the cause of earring phenomena. Okay. So, that means you will have, if delta r is more, okay, that means anisotropy in different direction is there, okay, then you will have earring phenomena. Okay. So, our purpose is to minimize or to bring down the delta r value. Okay. The another value of importance is called normal anisotropy, okay, and that is basically that what is the thinning characteristic of the material. Okay. So, if you have large value of r, okay, then it is good, okay, that means the ratio of width to thickness strain, that means there is a little tendency for thinning, okay, when you have a high r value, because if you see it is this particular relationship is slightly different. In the previous one we had a minus sign here, but here we have a plus sign. Okay. So, it is just a kind of an average r value. Okay. So, average r value, if it is high, then it is good, because then you will have less thinning tendency, okay, because our r is width strain divided by thickness strain. Okay. So, a high r value will be there when your thickness strain is small, that means thinning behavior is less, okay, and then you will have a high r value. So, if it is deviating from unity, okay, then it is an indication of normal anisotropy. This means there will be anisotropy behavior along the thickness. Okay. So, one is in different direction in the plane of the sheet, okay, and one is that you have different strain value in the width direction and the thickness direction. Okay. So, these two values determine the formability of the material. Okay. So, for a good formability, okay, I need a high normal anisotropy value, okay, and low absolute value of planar anisotropy are good for metal forming. Okay. And when you will have a higher planar anisotropy, then that which is not good actually, when if R0, R45 and R90 are not equal, then it means planar anisotropy exists in material, whereas R value deviating from unity is an indication of normal anisotropy, as I told you. Okay. So, I need a high normal anisotropy, high value of normal anisotropy and lower value of planar anisotropy. Now, what is the texture which is required for this kind of behavior? Okay. So, deep drawing steel, low carbon, desired property is good deformability with high R value, okay, and isotropic deformation with low delta R value, as I just told you, only they have taken a small r instead of capital R. Okay. So, you can take it as capital R, this is delta R. For this you need a 111 fiber texture with which is parallel to normal direction. Okay. So, as we have already seen the fiber texture, so you need a 111 fiber texture. Okay. In ferritic stainless steel, Fe 16% chromium, okay, good deformability as in 1, okay, and again 111 parallel normal direction topologically random distribution of grains. Okay. So, again you need a 111 fiber direction, which was the gamma fiber, if you remember we discussed in the previous lecture. If you have a electrical steel, now electrical steel the purpose is different, there the purpose is not the formability, but the purpose is to reduce the hysteresis losses. Okay. As you can understand that these electrical steels are used in transformers, where you have this primary and secondary windings. Okay. So, primary windings have 50 hertz electrical supply, that means 50 times it is getting magnetized and demagnetized as the current is flowing. Okay. So, if you have a very high hysteresis losses, okay, it means every second 50 times you are having that hysteresis loop. Okay. If you remember, you have a hysteresis loop like this. Okay. And in each loop, whatever is this area, that decides the energy loss. Okay. So, if energy loss is very high, then of course transformer gets heated up and also your efficiency will be low. Okay. So, for reducing this hysteresis losses, a particular texture component is required, which is called Gauss texture. Already we have seen this. Okay. So, if you have a Gauss texture in the plane of these small strips of the transformer, okay, then this particular direction, okay, is the easy magnetization direction, okay, and demagnetization also of course. So, your hysteresis losses will be low. Okay. So, for that the texture requirement is 100 parallel rolling to rolling direction, example Gauss texture, okay, which has a 100 parallel to rolling direction. Okay. However, whatever texture is required for electrical steel is usually not good for the formability, and whatever is required for formability is not good for electrical steels. Okay. So, as we have told that you need a gamma fiber is most suitable texture for formability, okay, and that lies here, which comes in 5 to 45 degree section, okay, and location is somewhere here, which is basically 111 plane, okay, parallel to ND. Okay. So, you can have different directions. So, for example, it is starting from 111 110 and the last one is 111 112. So, basically the 111 is parallel to ND, that is the component we need for good formability in steels. Okay. And if you have this, you will have lower planar anisotropy, okay, and that will be good for your earring behavior. If you see anisotropy in aluminum alloys, okay, effect of texture. So, minimization of earring can be achieved by mixing the cube and S texture. Okay. These two components if you mix, okay, then the earring phenomena is kind of a distributed throughout the you can say circumference. Okay. And the optimum volume ratio of these two is S and cube is 1.67:1 if you have this kind of mixing of the two texture components, okay, then you will be having a good formability. Okay. So, again you can see that where the this particular cube is of course will be at these locations, okay, at the corner locations, and S is you have at these locations. Okay. So, if you have a good combination of this S and Q, okay, you will be able to achieve a lower planar anisotropy, okay, and that will help you in the earring phenomena. This is another work of ours where we studied the anisotropy in friction stir processed aluminum alloy. Okay. So, in the first figure we have different texture components copper, S, brass, gauze and cube, okay, and on the y axis their fraction is noted down. Okay. So, basically these are the different FSP condition, friction stir processing condition. There is one module on severe plastic deformation later on. Okay. There we have discussed the friction stir processing in more details. Okay. So, you will be able to understand that what we are trying to say here. Basically this 30, 50 all these are traverse speed, okay, and MP here is used for multiple pass. Okay. So, we have done multiple passes here, okay, so that you are able to get a enough amount of sheet for doing forming experiment or doing anisotropy experiments. Okay. So, texture components are there, copper, S, brass, gauze and cube all are there, okay, and their fractions are noted on the y axis, and you can see that this is the planar anisotropy plotted for different condition. Okay. So, the multipass you can see that the planar anisotropy values are much lower than all the other conditions, okay, which is a good thing for sheet metal forming. Okay. And also the normal anisotropy value also is lower, okay, but reasonably high. Okay. so that you will be able to get the benefit of both lower planar anisotropy and high normal anisotropy. Okay. So, and basically you can see that what so there are two type of calculations done here. Okay. So, one is what we have done or what we have calculated from the actual experiment. Okay. So, you have experimental value and calculated anisotropy, experimental and calculated. So, these are shown, these particular ones are the experimental ones. Okay. And these are the estimated from the texture analysis. Okay. So, you have different texture component, they will affect the anisotropy property. So, you can see that there is a nice matching between the calculated anisotropy and the experimental anisotropy, both are increasing and decreasing almost in a similar fashion. Okay. And in multipass both are showing a very low value. Okay. That means the combination of texture component which is we have achieved in 30 and 50 megapascal. So, you have low cube is coming down. Okay. And similarly, if you see brass, copper is going up in case of this 30 megapascal, where you have the minimum planar anisotropy. Okay. For S also more or less same, but for 50 megapascal it is 50 multiplies 50 it is coming down. Okay. So, the effect of that you can see on the planar and this normal anisotropy. So, since it is achieved in the multiple pass frictional stress processing, so that is a very good condition for forming. Okay. So, with that this is again a short lecture on the kind of a case study or application of texture in mechanical properties. Okay. So, now we have seen that what do we mean by texture. Okay. And we also have seen that different processing condition give rise to different type of textures, okay, texture components, and this texture component ultimately affects mechanical properties. Okay. So, this gives you a complete picture that how the processing conditions affect the microstructure and texture. Okay. And then how that in turns affect the mechanical properties, that is the ultimate use of the material. For example, either it can be in case of forming process or it can be in terms of electrical steels. Okay. So, this should be a good example of control of different microstructural properties by processing and then seeing the effect of that on the properties. Okay. So, thank you for your attention.